So welcome to week 3 of AA203. So as per our usual roadmap, today and tomorrow will be still in the open loop quadrant of our roadmap. Specifically, last week we introduced the general concept of open loop control, which is to be kind of compared to with closed loop control, which will be the topic of next week. And specifically in open loop control, we kind of highlighted the fact that we are interested in an optimal control signal or trajectory, which is only a signal of the initial time t. So we are looking for an optimal control trajectory u of t. And specifically, kind of within these class of methods, we discussed that there are two macro kind of subcategories: indirect methods and direct methods. Last week, we introduced indirect methods, which, loosely speaking, kind of relate with, first of all, deriving optimality conditions for the infinite dimensional optimal control problem and solving for those. If you wish, kind of the analog we usually recalled was the one from finite dimensional optimization, whereby kind of the optimality conditions were akin to the gradient of f equal to 0 conditions. Of course, in finite dimensional case, those optimality conditions, so gradient equal to 0, boil down to a system of algebraic equations. In the case of infinite dimensional optimization, which is the one you're interested in for optimal control, these optimality condition boils down to differential equations, but the high-level picture is the same. And so today we'll be finishing our discussion on indirect methods, and then on Wednesday we'll be looking at direct methods. And specifically for today, we will start by extending the optimality conditions which we introduced last time, which assume that we had unbounded controls. And so today we will be extending those optimality conditions specifically for the case of bounded controls, which is a very common kind of constraint to have in practice when you're dealing with optimal control problems. And we will see how this will lead towards the kind of celebrated Pontryagin minimum principle. We'll then look at various different examples. Specifically, we'll be looking at some kind of archetype optimal control problems. First of all, to see how we can use these optimality conditions in practice and get familiarity with that, but also from the perspective of inspecting the kind of control profile that we get out of these optimality conditions. And then we'll conclude this part by looking at computational methods. So we have been describing indirect methods over and over as optimized then discretized methods, again in comparison to the direct approaches, which are discretized then optimized methods. And specifically the optimized part entailed with deriving the optimality conditions and solving for those differential equations, and the discretized part related with feeding those differential equations to a numerical solver, which is also what we'll be looking at with the computational methods. Okay, so just as a reminder, so last time we concluded by looking at this optimal control problem where we had assumed that we had unbounded controls. So again, to recap the notation here, we assume that we have a system described by the following dynamics. And the goal is to find an admissible control U star, which causes the system to follow an admissible trajectory, X star, that minimizes the given cost functional, which is a combination of a terminal cost, H, and a kind of stage cost, G, that is integrated over time. And indeed, we assumed that both the states and the control regions were unbounded. And this led into defining the following optimal necessary and optimality conditions, which at a high level entailed, first of all, defining the Hamiltonian, which, if you want, acted as the analog of the Lagrangian function in finite dimensional case, where the Hamiltonian is defined as the stage cost plus a term which represents our dynamics f times a vector of or a function of costates p of t, which again represents the analog of the Lagrangian multipliers. And in finite dimensional optimization, the Lagrangian multipliers were denoted as lambda. Here we denote these costates as p, which are indeed a function of time. And they're called costates because there is one costate variable or function for every state function. And so given that we defined this Hamiltonian, we saw how the optimality conditions boiled down to defining these set of differential equations. The first one representing trivially our dynamics. So if we take the partial derivative of our Hamiltonian with respect to the co-state variable p, we get our dynamics, so x dot equals f. The second two set of equations are less intuitive, but we saw how the second one essentially boiled down to p dot equals the minus the partial derivative of the Hamiltonian with respect to x. And then we saw how the third set of algebraic equations represented a stationary condition of the control with respect to the Hamiltonian. And so, essentially that the derivative of the Hamiltonian with respect to u needs to be equal to 0. And we saw how in practice this boiled down very mechanically towards usually using this last set of algebraic equations to express u as a function of x and p. We can then do the appropriate substitutions in the differential equations, which we can then solve. To solve these differential equations, we saw how this generated, kind of boiled down into having to pinpoint a number of constants of integration. And we saw how we could use boundary conditions to pinpoint those constants of integration. Usually, the initial boundary conditions are given. So we know the state at time 0, and we know what the time 0 is. But the boundary conditions at the final time depend a bit on the scenario that we're looking at. And so we saw how we could use this kind of master boundary condition depending on whether the final time or final state is free or fixed. For example, if the final state is fixed, it means that there are no admissible variations, delta xf, we can do. And so all of this term goes to 0. And so we're left with this other part of the boundary condition, and vice versa. Any questions until this as a general recap of where we are? Okay. And indeed, so as I mentioned before, so far we have assumed that both the admissible controls and states are not constrained by any boundaries. But in reality, kind of states and control constraints are actually extremely common in practice. So for example, kind of a classical control constraints might model that we have some limits in our actuation. So again, we cannot impose like a thrust that is infinitely large. And also state constraints might be quite common. For example, just to give you an idea, kind of a classical state constraint might represent obstacle avoidance. So where we want to avoid some kind of obstacle in the physical space. Now, for the purpose of this class, we'll focus on including the case of bounds on the controls. And we will not discuss the case where we include the bounds or constraints on the states. First of all, because the kind of mechanics become substantially more complex. And also because in practice, indirect methods are not really the tool of choice to handle constraints on states. So what people usually do would maybe cast the problem as a motion planning problem, where you're kind of abstracting away from the dynamics, or at least simplifying the dynamics, and more geometrically solving the trajectory optimization problem. And then you're using those insights that you get from these more abstract solutions to inform your indirect methods. So long story short, but what we're saying here is that we want to expand our analysis, and we're going to focus on the bounds on the controls. Yes?
Last lecture where we were using the conditions for optimal control modes you had in the previous slide, and then we had a t final equals some expression in terms of A. You were saying that was that actually when we solved that problem, did we actually find an optimal control, or is it what you're saying that mu could be anything, therefore TF could be anything? And now we're going to introduce.
What setting are you referring to?
In previous lecture, we did an example. We found a T final. Mm-hmm. It's in terms of alpha.
Yes.
Did that correspond to some particular optimal control, or is that what you're saying, that it was unconstrained? So the control could be anything, and therefore the T final could be anything?
No, so in that case, we actually solved the problem completely. So in the slide, I only highlighted the final time, TF, which was like a complex thing, like over 1800 or something like that. But of course, once we solved the for the necessary optimality conditions. So once we solve the differential equations, we have everything. So we have x, we have p, and usually the controls are a function of x and p. And so by just substituting those x and p that we get by solving the differential equations, we would get the shape of our control. So here what I mean by bounds on controls is that we would have something like the absolute value of u needs to be smaller or equal than 1. Something like that. Does this clarify?
It's possible that because we didn't have the constraint in the other problem, that for some given alpha and b, it could result in an optimal control that violates a constraint.
Yes, of course, there we were not imposing this constraint, so we are not really sure about the, if we're respecting any kind of constraint like this. Yeah, but it'll be clear in a couple of slides because we'll be making some concrete examples. Okay. So now, before kind of showing you how the optimality conditions will change, I just want to give you a small kind of insight into why the bounds of control on the controls kind of complicate the analysis. And the way we'll kind of build this intuition is by, as usual, referring to the finite dimensional case. And so, recall from our discussions on finite dimensional optimization, where in order to derive the optimality conditions of the gradient of f needs to be equal to 0, we started by looking at the increment of our function with respect to some displacement delta x. And we saw how this could be well approximated by our function f of x plus the gradient of f transpose delta x, or we call this the differential, plus some high order terms. Right? So, and essentially by just bringing the f of x on the other side of the equation, what we get is that the increment of our function is well approximated for the small delta x's by our differential, so the linear part of our approximation, of our Taylor expansion. And we know that for a point x to be a candidate local minimum, what it means is that for any displacement delta x that I make, this increment has to be greater or equal than 0, right? So wherever I move, I'm increasing the value of my function. Now, in the unconstrained case, we were able to translate this expansion so that specifically that the differential has to be greater or equal than 0 to the fact that in order for this to be greater or equal than 0, since I can take any possible displacement delta x, both in the positive and in the negative direction, the only way for this to be both greater than equal than 0 or less or equal than 0 is for the gradient of f to be equal to 0. Right? So this is essentially what we said a couple weeks back. Now, visually, what this means is that if we have a function that looks something like this, and assuming I'm not considering the boundary points of this function, the gradient of f equal to 0 essentially gives us a mechanism to isolate candidates for local minimums, right? Where specifically in this case, 1 is a local minimum and 2 here are local maximum. But still they're candidates, right, according to our optimality conditions. Now, what happens if we do consider the boundaries here? So, is this a local minimum? I see some noddings. Can you say why this is a local minimum? Yes.
Because if you move anywhere on that curve, that's still within your boundaries.
Exactly correct. So in this case, remember that here we're defining minimums are as whatever movement admissible delta x I take, I'm increasing the value of my function. In this case, the only displacements I can take are ones on the positive direction, on the right. And so for all of these displacements, the value of my function is greater. Right? So this is indeed a local minimum. Same thing for this other point here. of course, kind of mirrored, where the only displacements that I can take are in the negative direction. So you see that when I'm considering these boundaries, kind of the condition that the gradient of f is equal to 0 doesn't really cut it anymore, right? And so going back to this math, kind of what we know in the bounded case is that this has to hold, right? But we're not able to do the kind of the point that these displacements can be both in the positive or negative direction, but they depend on the boundary. And so the optimality condition in this case is that the differential has to be greater or equal than 0. Now, this complicates kind of a series of other discussions when we actually want to make this actionable, but this is the kind of difference that it makes in the finite dimensional case. In the infinite dimensional case, when we move to optimizing to calculus of variation, the exact same intuition applies. And specifically, remember that we derived the optimality conditions, again, starting from the variation of our cost functional j, which we denoted as delta j. And in order for a candidate u star to be a minimum, or a relative minimum, we want that this increment is greater than 0, right? So exactly as in the finite dimensional case. Now, what we did last week is that we approximated this increment through its linear term, or the variation, delta j, plus some higher order terms. And then we used the fact that these delta u's could be arbitrary to derive the fundamental theorem of calculus of variation, that is that delta j, so the variation delta j needed to be equal to 0. Right, so I trust that you're kind of seeing the analog here. Now, when we talk about kind of, let's open a small parenthesis. When we talk about variations in calculus of variation, so what does delta u look like? Because a displacement in delta x kind of intuitively makes sense, but here we're talking about functions, right? So delta u itself is a function. So if you want visually, say that we have a function over time, and that we have some kind of bound in our controls, which we denote as u bar, meaning that our controls cannot go above this bound. Our control u of t might look something like this, where for some time we are in the admissible region, then we are still admissible but at the boundary, and then perhaps we could go down, right? So this could be a potential control function ut. So a displacement delta ut in this case is a function in itself, right? So it could be any variation that I do to my function ut. Now in this part of the region where I'm not at the boundary, the variations that I can take could be both delta u, but also negative delta u, right? So variations is both directions are admissible. But in the case where where my control lies at the boundary, then here I can only take the variation only on kind of one-sided, if that makes sense. And so what this boils down to, and in general, whenever I'm trying to optimize some kind of, could be final time, given some constraints, it is very common that you, for some portion of my control profile, I will be at the boundary at some point. And it turns out that if the optimal control lies on a boundary, then the necessary conditions, similarly to how it did in the finite dimensional case, essentially boils down that the variation delta j has to be greater or equal than 0. Any questions on how we got to this update to our conditions? Yes?
Sorry if you mentioned it before, but on that lower plot that you have there, what was the connection to that expression to the you could only vary in one direction point?
Sorry, can you repeat the question? So here?
Yeah, I think I'm confused how that would be a situation where you could only think you said something like vary in one direction in a certain case.
Yes, no, it's a good question. So remember that a lot of the kind of logic that we're following when we're doing those statements over there was that the admissible variations were arbitrary, right? And so this allowed us to essentially derive that the variation of j, so delta j, has to be equal to 0 in the fundamental theorem of calculus of variation. So here I was trying to kind of visualize what does it mean for, first of all, to be a variation in the space of functions, but then also what does it mean for a variation to be bounded so that it's not arbitrary, right? So in this space of my control function, here my variations are actually arbitrary. So admissible variations are arbitrary because I could go in both directions. Here, when my control is at a boundary, I cannot displace my function in the positive direction here, right? Because I would violate my bound. Yeah. And so the only thing that I meant here is that the boundaries essentially break the assumption that my variations are that any variation is admissible. And so this does not allow us to make the statement that the delta j is equal to 0. Yeah. Yeah. Okay. Now, this, of course, then you can imagine that the consequences of this is on our optimality conditions are that we have to strengthen our condition on the control U. And specifically, these are the updated conditions, which are referred to as the Pontryagin minimum principle, where we are, as it is highlighted here on the slide, we're essentially updating and strengthening the condition on the stationarity of our control U. So everything stays exactly the same as the conditions that we saw before, with the addition that, or kind of modification that before, the optimal control U had to be a stationary point of the Hamiltonian, so the gradient of h with respect to U had to be equal to 0. Now we want the optimal control U to be a global minimizer of the Hamiltonian. So essentially, the Hamiltonian evaluated at the optimal candidate U star is smaller or equal than the Hamiltonian evaluated at any other U of t, admissible control U. Of course, there is a jump from the fact that the variation has to be greater or equal than 0 towards the updated optimality conditions. But kind of the bottom line here is, again, we want to be kind of pragmatic and functional. And when we introduce bounds on our controls, it boils down towards updating and strengthening some of our optimality conditions, which in this case entails having to minimize the Hamiltonian rather than only being a stationary point. Any questions here? Again, mechanically, we kind of provided some insight into what is more complex the moment we consider bounds on controls. And then we stated the updated optimality conditions. Okay, so let's now make an example to kind of operationalize these updated optimality conditions. Okay, and so specifically here we're looking at the following system, which is a second-order system with kind of linear dynamics, and where we want to optimize the cost functional that is represented as a kind of squared cost functional, a quadratic cost functional. We are assuming that the final time is fixed and the final stage is free. But note that here now we are introducing this bound on the controls, specifically that the absolute value has to be less or equal than 1. When we are, so these type of problems, that is when we are trying to minimize the squared of our controls, so our quadratic costs, are also known as minimum energy problems. Yes?
The definition from the previous slide. What does it mean to say that your, you know, the inequality of H of all the stuff star is less
Yeah.
than equal to.
Yeah.
What does it mean for you not to be optimal? It's like X and P to still be, like how can you have a non-optimal U but then an optimal X optimal?
So in general, remember that these are a set of conditions for any candidate triplet of states, controls, and co-states. Now, the first two are differential equations. Here, we are basically strengthening the algebraic conditions, which essentially entail that the controls, the candidate control U had to be a stationary point for the Hamiltonian, given X and P. And in this, we are basically strengthening that condition, whereby you should basically see that we are trying to minimize this function only as a function of U, right? So given some X and P's, we are finding the global minimum with respect to U of H.
Given some U, it might not be.
Yeah, if you want there, you could also interpret it as U star needs to be the argmin of H of X star U P star. Right, so this is basically saying that for any candidate U star T, it has to be a global minimizer for any other U of T that I could replace it with. Yeah.
We're now highlighting that this is a global minimum. Was it not the global minimum before?
Before, we only needed that U had to be a stationary point of the Hamiltonian. We only enforced that the derivative, the partial derivative of the Hamiltonian with respect to U had to be equal to 0. Now we're actually enforcing that for kind of the strengthened condition, U not only has to be a stationary point, but it has to be a global minimum. Maybe one, so I know that we kind of took kind of a big jump in defining this strengthened condition, but maybe one way in which you could relate this condition to the one we had previously, that is how to relate the global minimization of the Hamiltonian with respect to U and the stationary point condition, is that, so this condition is essentially strengthened because we are introducing bounds on controls, right? Now assume that we are kind of loosening these bounds on the controls so much. So visually, if you remember here, we had this kind of U bar, which represented our bound. We are increasing it so much that it's not an issue anymore for our problem. If we are increasing it so much that it's not anymore an issue for our problem, then any kind of global minimum of our Hamiltonian is also a stationary point, right? So there is a link here in the sense that if our control bounds are so loose that they're not an issue anymore, then a necessary condition for control U to be a global minimum of H is it to be a stationary point. No, this is just like a mental exercise, just to show some kind of link between this formulation and the one we had previously. Did this confuse even more? Okay. Again, bottom line here is that we want to define these optimality conditions. Now we are, compared to the one where we had previously, we are introducing some bound on the controls. These bound of the controls boil down to having to strengthen this third algebraic kind of condition. Before, it was just enforcing that U had to be a stationary point of the Hamiltonian. Now we want U to be a global minimizer of the Hamiltonian. Yes?
In the last example where we wrote boundary control inputs, we would, like if our third condition, we would use to find the optimal control inputs and then plug those into the differential equations for X and P. But I'm having trouble understanding how we would optimize over, the Hamiltonian, like as if we already knew the optimal state and like X star and P star. Yes. Because I assume that the X and the control inputs and the states are coupled.
Yeah, it's a great question, and it'll be clear, I think, one slide from now, because we're exactly solving a problem, and so you'll see how we do it. The bottom line is that obviously this is complicating things, because before it was just enforcing an algebraic equation where we would express x as a function of u as a function of x and p, and then doing the substitution. Now we will be solving this, we will basically have to solve an optimization problem and derive a solution of u as a function of x and p, and then doing the substitution again. So mechanically, it doesn't change much. It's just more complex because before it was enforcing an algebraic equation. Now it's solving an optimization problem. Yeah. Okay. So indeed, we want to approach this minimum energy problem where now we have some bounds on the controls. And specifically, again, we want to be, as usual, we want to be methodical. So we define the Hamiltonian as 1/2 x1 squared plus u squared. And here I'm omitting dependency on time, just to save some ink. Plus the costate times our dynamics function f, p1, p2, transpose x2 minus x2 plus u, which we can write as 1/2 x1 squared plus u squared plus p1 x2 minus p2 x2 plus p2 u. Okay. So this is just our Hamiltonian. Now we want to enforce our third condition, that is that u has to be a global minimizer of the Hamiltonian. So the new condition that we just strengthened. So we basically want to solve this problem here, right? So u star has to be a global minimizer of the Hamiltonian. Now, if this is the Hamiltonian, the only terms that depend on u's are these two here. And so this problem essentially boils down to minimizing over u 1/2 u squared plus p2 u. Is the marker strong enough this week? Not really? All right. Let's try this other one. I love the variance of this. Yes. Okay. All right. So, but can you read this one here? Anybody that cannot read it? Okay. All right. So notice that this is a quadratic function. So in order to minimize it, we can just set the gradient of this equal to 0. Right. So we can just set the gradient with respect to u of this thing here. So of 1/2 u squared plus p2u equal to 0, which essentially means that u plus p2 has to be equal to 0, and so u star is equal to minus p2. Right, so now to answer to your question, you see here we solved an optimization problem. The output of this optimization problem is still expressing u as a function of only p in this case, but in general it could be a function of x and p. Okay, now we have to analyze, so we have u has some bounds, right? So we have some bounds on the values of u. And so we need to basically look at different kind of case-by-case studies. So specifically, we will be looking at 3 cases where our bounds are that u has to be between -1 and 1. And so we'll be looking at the case where this global minimizer, minus p2, is smaller than -1. We'll be looking at minus p2 being between -1 and 1, or the fact that minus p2 is greater than 1. Right? We'll be looking at these 3 cases. Because ideally, the optimal control will be negative p2, but there are some bounds on u that we have to respect. Visually, if you want to have a sense of what is happening, this is a quadratic function. So something that looks like this. The minimum is at negative P2. And now we'll be analyzing different cases depending on where P minus P2 falls. So the most obvious one is if minus P2 is feasible, so it falls between negative 1 and 1. So say something like this. Then the optimal U would just be minus P2, right? Now say that negative P2 is smaller than minus 1. So we are in a situation where this is negative. Say that 1, 1 is here. What will be the optimum in this case? The optimal U in this case? Right, so this is the function we want to minimize, which is our Hamiltonian. We can only choose within minus 1 and 1. So in this case, where would the minimum be? Yes? Yeah, exactly. So in this case, the minimum would be minus 1. And you can imagine kind of a similar argument if negative P2 is greater than 1. So the interval now sits on the left of negative P2. And the minimum here would be 1. Right, so essentially now we have solved the third and strengthened condition. So we found the global minimum of the Hamiltonian with respect to U. And now we basically have what we need, right? Because now we have an expression of U as a function of x and p. In this case, only the costates p, which we can substitute in the differential equations above, feed them into a solver, and get the solution out. Interestingly, and this is, I think, one of the kind of strong points of indirect methods, is that regardless of the solution, so what the exact control is, we have basically pinpointed the structure of how our control looks like, right? So now let's plot our control U as a function of P2. What we have now is that our control in between minus 1 and 1. So if P2 is between minus 1 and 1, it'll basically look something like this. On the other hand, when it is below negative 1, it will be saturating at 1. And when it is above 1, it will be saturating at minus 1. Right? So our control profile is essentially linear and saturating after some point. Now, of course, in the moment where we didn't have those bounds, our optimal control would just be the linear part. Right? Okay, any questions on this? Yeah.
I understand this is like the third condition of the Pontryagin check. What about the other two?
Yes, it's a good question. So basically now here we express U as a function of x and p. The mechanics of this go that then we take this expression, we substitute it in the other two differential equation conditions, and we get some differential equations which we then solve either analytically, as we did last week, or as we will see today, through numerical solvers.
So this is like the next step?
Yes. Yes. So here we basically stopped halfway there. So we just derived the profile of U. So we just strengthened condition. If you had to go kind of all the way through, you would substitute this in the other differential equations and solve those differential equations. Here we just stopped here, but already said that already at this point, we can basically inspect the structure of our control. Because whenever we will solve those differential equations, we will get x's and p's. And those x's and p's, in this case, only p, will allow us to pinpoint our actual control, which, regardless of the value of p, will look like something like this. Right?
How do we use the p as escape screen?
Those will be used to pinpoint those will be boundary conditions, which we use to pinpoint the constants of integration in our differential equations. Yeah. Yes?
So like for the example graph that you drew there to kind of explain how you found conditions, what would, like, is the x, I'm just, like, what axis represents what? Like, which one is u and which one? Or am I just misunderstanding?
Yeah, so this would be u, and this would be kind of the Hamiltonian as a function of u. Does it make sense? Okay. Any other questions on this? We will see 3 more examples. So now we'll go through a few of these cases. Okay, and so indeed, so exactly what we get is this kind of control, right? So essentially what we derived here on the slide, on the whiteboard. So as a caveat, Pontryagin and colleagues derived some additional necessary conditions depending on kind of the exact structure of the problem. These are not too relevant for us for the purposes of this class, but I just wanted to mention that there are some additional optimality conditions that were derived. Specifically, if the final time is fixed and the Hamiltonian does not depend on explicitly on time, then the optimality condition is that the Hamiltonian has to be constant for all times between t0 and tf. And on the other hand, if the final time and the Hamiltonian is free and the Hamiltonian does not depend explicitly on time, then the Hamiltonian has to be equal to 0 for all times between t0 and tf. Now again, do not read too much into this. This is just, I wanted to use this as an example to mention that there have been developed additional optimality conditions, which at the end of the day are useful to pinpoint even further the structure of your solution. So there are a number of optimality conditions which have been developed, and these are additional ones compared to the ones that we showed before. And if your problem falls within these buckets, then the more optimality conditions you have, the better, because you can characterize even further what your optimal solution looks like. Okay, so what we'll be doing now is that we'll be looking at 3 archetypes, essentially, of optimal control problems. Specifically, we'll be looking at minimum time problems, so get to your goal as fast as possible. We'll be looking at minimum fuel problems, where the costs will be to minimize the absolute value of the control effort. Again, you could see this as the analog of minimizing thrusts if you're looking at like aerospace applications. And then we'll be looking at minimum energy problems. And so starting from minimum time problems, we'll be looking at the case where, indeed, we have some bounds on the controls. So the control U has to be between some lower bound, mi minus, and some upper bound, mi plus. And we want to drive a control-affine system. So for these examples, we will always be assuming the exact same system, which is a control-affine system in the sense that it linearly depends on the control ut. But this may potentially depend non-linearly on the state x. And this is because the A and B might be non-linear in x. But this still, so it is fairly general, kind of a dynamical system and formulation, but it does simplify slightly things because it is linear in the controls. And again, the purpose of minimum time problems is to get to a goal as fast as possible. In this case, we want to start from an arbitrary state x0, and we want to reach the origin. And the way we encode this minimum time, kind of the minimization of time in terms of a functional, is that we want to minimize j, which is just the integral between t0 and tf of 1. So we're just summing time, essentially. Yes?
Here, is it like a time index, or is it like a different possible admissible control?
We are assuming that u here could be kind of multivariate. And so we have m control variables. Yeah. Yeah, yes. So imagine maybe you can accelerate in different directions, and for each of those dimensions you have some limits. Okay, so let's apply what we know to solve this, this problem. Okay. So as usual, we want to start from our from defining the Hamiltonian, right? So the Hamiltonian for us entails the stage cost g, which for us is just 1, plus the costates times our dynamics, right? And so in this case, it will be P transpose A plus PU. Now, just as a notation, here we will express B, the matrix B, as in terms of its columns. So we can just rewrite B in this way. Which essentially means that this is equal to 1 plus P transpose A plus the sum that goes from I to M of B I U I. And this is because then this product here essentially entails, becomes the linear combination of its columns, essentially. Okay. And we can rewrite this as 1 plus P transpose A plus the summation that goes from 1 to M of P transpose BI UI. Right? Okay, so here we just wrote our Hamiltonian. Now, as we did before, we want to start from the third, or optimality conditions, which in this case, and according to the Pontryagin minimum principle, it means that we want to find U that is the global minimizer of the Hamiltonian. So, as usual, U star will be the minimum with respect to U of the Hamiltonian, which, again, out of these three terms, only the last one depends on U. And so this essentially means that we want to minimize U of the summation between Y and M of that term over there. So P transpose BI UI. Now, the controls are something that we pick, and these are independent, according to our problem formulation, across M. Right? And so minimizing the summation is essentially equivalent to minimizing the individual summation terms for all i's that go from 1 to M. And so this basically maps to minimizing over UI of P transpose BI UI for all i's that go from 1 to M. Okay, now, does this make sense? Yes. Now, how do we minimize this, right? So, again, I think it's good to consider different cases. So, specifically, our optimal control U star will depend on whether P transpose BI is positive or whether P transpose BI is negative, right? So if P transpose DI is positive, what is the minimizer U in this case? right? So we want to minimize this term over here as a function of u. This will depend on what this term in front of u is. And so if this term is positive, and u has to be between mi minus and mi plus, how would you pick u in this case? Yeah, correct, exactly. So mi minus, right? And of course, kind of by mirroring, in case p transpose bi is negative, what is u here? It will be the upper bound, right? So mi plus. Now, are we missing something here? Yeah, exactly. And the point here is that for P transpose BI, if for optimal controls for which P transpose BI is, or optimal triplets, so optimal X, U, and P, for which P transpose BIs is equal to 0, the optimality conditions do not give us any characterization of any information about what the optimal control looks like. This is kind of a condition that is referred to as singular arcs or singular conditions, which essentially says that the optimality conditions for some kind of characteristics of our triplet do not give us any information about the optimal control U. Now, for the purposes of this class, we won't be dealing with singular arcs, and so this is not a problem that should bother you too much. But I just wanted to kind of use this example as indeed an example of the kind of problems that could emerge, whereby in this case, there could be the situation where my optimal actually lies in a situation where for some portion of my time, P transpose BI is equal to 0, and so I would not know how to characterize my controls. Now, there could be some much more sophisticated math in order to pinpoint the behavior of my controls. In this case, it is easier for linear systems. It becomes much problem-depending kind of solution in the moment where you're looking at non-linear systems. But I think it's just important for you to know that there might be situations where these problems emerge. And in a way, this is actually where most of the brain power, when you try to use indirect methods, goes into, is tackling these kind of ill-conditioned situations. For us, assuming that the optimal, for our optimal control problem, so the optimal triplet X, P, and U does not fall into the singular arc conditions, we basically have determined that our control has this form here, which is also known as bang-bang control. And this is because essentially the control has a profile that either accelerates kind of at max velocity or brakes at its maximum. And if you think about what we're doing here, that is minimizing final time, it kind of makes sense, right? So we have some linear system or a control-affine system. We want to minimize time, and so we're not messing around, right? We either go for full throttle or we brake at our maximum speed. Yes?
Is equal to 0, does that not necessarily mean that it's uncontrollable in that state?
It means that the optimality conditions do not give us a characterization of how the control looks like. So remember, all of these are optimality conditions that allow us to pinpoint candidates for optimality. And so this means that in those situations, these optimality conditions do not give us information on what an optimal looks like. Yeah. Yes?
What these singular arcs, like what types of problems these are unique to?
They're not unique to specific problems, but singular arc or singular condition refers to those situations for which the optimality conditions are not able to characterize the control, essentially.
It's not unique to the application of the Pontryagin.
Yes. So if you're applying the Pontryagin minimum principle, that is the optimality conditions for optimal control problems, you might end up in situations like these where at face value, we don't have enough information to characterize what the control looks like.
Sorry if you said this already, but I'm just confused. Did you get that the controller is a bang-bang controller from minimizing the the Hamiltonian, or like the problem gave you that this is a thing?
So again, I think the mental mindset you should be in is that we are being extremely methodical. So we have an optimal control problem, and we follow the recipe. So the recipe entails defining the Hamiltonian, and then enforcing the optimality conditions. The way we mechanically go through the optimality conditions is by starting from the third one, which is in this case, finding U's that globally minimize the Hamiltonian, which leads us to this. If we were to continue, we would then take this and substitute it in the differential equations. We would then solve those differential equations and get the full thing. Here we're again stopping before the solution of the differential equations. That is, we only get the global minimum of the Hamiltonian, and this already gives us the profile of our control signal, right? Which in this case is bang bang, because we already know that we will basically be at the maximum control on the boundaries of our control at all times, essentially. Kind of removing the singular arc discussion. Okay, and so essentially we showed what to do when P transpose B is different from 0. It is not obvious what we do in the equal to 0 case, and we discussed this. We refer to these situations as singular conditions or singular arcs. And if you're interested in learning more, the textbook from Kirk we were referring to last week is indeed a good reference for this, because it has some discussions. Okay, so now we move towards a second kind of archetype, optimal control problem, which is minimum fuel. So in this case, we have the same boundary bounds on the controls. We have the exact same control affine system, but now we are changing the cost, whereby we start from an arbitrary x of 0. We want to reach the origin in a fixed time. So now time is fixed. It's not a variable we're optimizing over. And we want to reach the origin by minimizing the absolute value of the control. And these types of problems where we're minimizing absolute values of the controls are usually referred to as minimum fuel problems. Okay. So again, let's follow the usual procedure, right? So we define the Hamiltonian, which in this case, G for us is the sum from 1 to m of Ci times the absolute value of Ui, plus P transpose A, plus the sum that goes from 1 to m of P transpose Bi Ui. Here I skipped a couple of steps, but this is exactly because the steps are exactly the same as the ones we did before. So we express B as in terms of the columns, and then that product essentially becomes the linear combination of the columns of B. Is it clear how we define the Hamiltonian here? Okay. So now we want to enforce our optimality condition such that the U has to be a minimizer of the Hamiltonian. And again, in this case, the only terms that depend on U are the first and the third. And so this boils down to taking the minimum over U of the sum that goes from 1 to m of Ci times the absolute value of Ui plus P transpose Bi Ui. Right. Now again, the dimensions of U are independent, and so we can do exactly the same trick that minimizing the summation is equal and equivalent to minimizing the individual summation term for all i's from 1 to m. And so this means that it's equal to minimizing over ui's of Ci times the absolute value of Ui plus P transpose Bi Ui And this is for all i's from 1 to m. Right. Okay. So now let's write this term slightly more nicely. So this is equal to Ci plus P transpose Bi times Ui if Ui is greater or equal than 0. And it is equal to negative Ci plus P transpose Bi Ui if Ui is less or equal than 0. Okay, and so we want to minimize this object, and again we have to go in a kind of case-by-case analysis. So if P transpose Bi is greater than Ci, what happens is that this term is positive. And so what U would I pick here if I want to minimize this term? Sorry, I think I heard a 0. Yes, which is correct. Did I hear you even something else, or no? So indeed, it is 0. And so indeed, so in the case where P transpose Bi is greater than or equal to Z, then greater than Ci, this is greater than 0, which means that in this case I would pick Ui equals to 0. If we're still in that case, then this other condition would also be positive, right? So this term here is also positive. And so here the Ui that I would pick would be Mi minus, right? And so in between these two cases, then for kind of this case here, Ui star would be equal to Mi minus, right? Now we do another case, that is the case where P transpose Bi is between 0 and Ci. If this is the case, this is still positive. So here I would also pick Ui equals 0. If B transpose Bi is between 0 and Ci, this term here is negative. And so Ui, the Ui that I would have to pick would also be 0 to minimize, right? And so essentially in this case, U star I is equal to 0, right? Now, just by mirroring, we would go through the other two remaining cases, which essentially are that P transpose Bi are between negative Ci and 0, and the fact that P transpose Bi is smaller than negative Ci, right? So these would be the other two cases. And here we would get that Ui star is equal 0, and that Ui star is equal Mi plus. This is just by mirroring, right? And so again, kind of we reached a point where we have expressed U as from the third of our boundary, from our necessary optimality conditions. And we see that we are we are assuming we're not in the singular arc conditions. So we are ignoring the equal cases of these examples here. But we have again pinpointed the structure of our control profile, right? And this is the one that you can see here on the slide, where Ui, depending on the value of P transpose Bi, is essentially either at its minimum value, or 0, or at its maximum value. And this is known as bang-off bang control. And if you think about what we're doing here, it is quite intuitive again, right? Because this essentially describes control profiles where I want to get as quickly as possible into a state where I'm essentially coasting through my dynamics, where I can do nothing, essentially. And then maybe only at the end do another impulsive control. And this aligns with the objective of minimizing fuel. Any questions on this example? I think here it's kind of easy to kind of get lost in the technicalities of solving this minimization, but I hope that at a high level what we're doing is starting to become clear, because we're essentially repeating ourselves over and over, where we're enforcing our optimality conditions by defining the Hamiltonian, optimizing the Hamiltonian with respect to u. This gives us a control profile, which in order to kind of solve the problem fully, we would have to then do the appropriate substitution and solve the differential equations. But this already gives us a way to analyze the structure of our control profile. Yes?
Yeah, sorry. So when you were doing the CI plus PTBI, that is just you getting that derivative and saying, like, that just gave the derivative based on, like, whatever the absolute value is. And then you were looking at the different options of PTBI greater than CI. I'm a little bit confused how then you got that it is there with a minimum based on PTI greater than CI. Because if PTI is greater than that's just a positive value, so then you said UI is just 0. And then so why is it now then the minimum?
You're talking about this case here specifically? Yes. So here, remember that our function we're optimizing is this one here, right?
Yes.
So it's a function where we have an absolute value.
Yes.
And so we kind of rewrote it according to these two cases.
Yes.
Now we are doing the case where P transpose Bi is greater than Ci. And we want to find the minimum across both of these values, right? So if P transpose Bi is greater than Ci, this is positive. And in the case where Ui has to be greater than 0, the minimum would be Ui equals 0. In this other case, this is positive. Ui has to be less than 0. And so the minimum would be Mi minus. The minimum between the two of them is when Ui is Mi minus.
Thank you.
Okay.
And will this have three singular arcs where obviously it's still the 0 case, but also when it equals Ci and negative Ci?
Yes. Indeed, here we are assuming that our optimal control does not fall into these conditions. Yeah.
Conceptually, I'm wondering, in the bang-off bang control sequence, is there something in those terms that also weighs total time, or is it purely just minimizing fuel?
This is, if you look at the objective that we were doing, we didn't have an explicit minimization over time, but time was fixed. Right? Yeah.
That makes sense.
Okay. So the third case of the minimum energy problem, I would just go through this quite quickly because it's exactly the same case as the one that we did on our kind of parabola and the negative P2 that we did just after the definition of the PMP. So I would go through this quite quickly. Again, here the cases that we're minimizing are squared cost functional. And we would be doing the exact same steps where we define the Hamiltonian. This Hamiltonian, because of we are assuming that R is positive definite and diagonal. And so because of this, everything nicely decouples. And so we get the same situation where minimizing these summation terms is equal to minimizing an individual term of the summation. And so since this is quadratic, we set the derivative of this equal to 0. And we will get this optimal control, which is exactly the analog of the negative P2. So this is why I'm kind of coasting through this, because this is exactly the same. And so we would get our saturating control, which is the case we were looking at the beginning. Right? So we had our control saturating when it's out of bounds, linear, and then saturating again. Yes?
As a diagonal matrix, that makes the calculation straightforward. Why is that justified?
I mean, R, if you think about it, it's a term we pick because we are defining the cost that we want to optimize. And so usually it's good to express diagonal cost matrices because it makes things easier. But we could also pick an R that is not diagonal. Yeah. Okay, so I have only 10 minutes left, so I'll skip over this and finish it next time. But I want to give you a hint on computational methods and show you how to solve these problems in practice. And so basically, until now, what we did is that we used our optimality conditions to derive our systems of differential equations and our minimization over U condition. And then we always kind of stopped at either we solved them analytically, as we did last week, or here we stopped at expressing U as a function of X and P's. And then we kind of said that here we would substitute these back in our differential equations, and we would solve them through numerical solvers. And at a high level, numerical techniques to solve two-point boundary value problems kind of divide themselves between indirect shooting methods and collocation methods. Now, we won't go into the details of how these models, these techniques solve two-point boundary value problems. But at a high level, you should see a shooting method as basically a method that approximates a two-point boundary value problem as an initial value problem, where I take a guess of what the initial value is. I kind of propagate my system forward. I see my error with respect to the final condition. I will get a residual, and then I update my guesses kind of iteratively. Indirect collocation methods, on the other hand, approximate the system dynamics through basis functions, for example, polynomials. And they enforce the dynamics and the boundary conditions at some specific points, which are called collocation points. And so these are, again, don't read too much into this, but this is just, if you want to open the box of how these numerical solvers typically operate, they're either implementing a shooting method or a collocation method. And we will be looking at our example that it also came up earlier today, where we are essentially optimizing the particle on a line. And we solved this analytically, where we basically derived the value of TF. But before getting there, I wanted to just briefly introduce, kind of in an abstract example, how these numerical solvers look like. And specifically, we'll be using the solve BVP method in SciPy, where kind of at a high level, the solve BVP essentially takes in a fun argument, which represents the right-hand side of our dynamics. BC, which represents the boundary conditions, expressed as the residuals of the boundary conditions. So it has to be something equal to 0. T, which is like a mesh of time, meaning we are discretizing time according to some discrete bins. And so this will be just a sequence of discretization time steps, which is just a series of increasing numbers. Z will be our aggregated variable. Essentially, here we will have all our states and constates kind of stacked together. And so kind of to see this in practice, let's look at simple examples, like the one here on the slide. So again, kind of as I said, kind of what these solvers usually take is this solve BVP, where we need to define, first of all, the functions, so our differential equations. And in the example that we're looking at, we have this system where we have Z1 dot equals Z2, and Z2 dot equals negative absolute value of Z1. And so here we're just basically stacking those dynamics. So we have, remember that in Python, counting starts from 0. So we basically have that Z1 dot is equal to Z2. So here we're just saying Z2. And then we have Z2 dot equals negative absolute value of Z1. And so we have negative absolute value of Z1. Now, we need to enforce our boundary conditions. which are that z1 at time 0 is equal to 0, and z1 at time 4 is equal to -2. And so what we have here, so ZA is intended for the boundary conditions at the initial time. And so we have ZA0 equal to 0, which is essentially this term over here. And then we have Z14 plus 2 equals 0, because we have to express them in the kind of residual form, which is what we have here. Now we construct the T mesh, which essentially is, again, just a number which informs what is our discretization of time, in this case from 0 to 4, and we assume we have 5 bins between 0 and 4. And Z-guess is just an initial guess of our variables at those times. So what happens if we just run this is that basically we get that the differential equations are solved. So this is the plot of Z1 and Z2 over time. So first of all, it goes from 0 to 4. And note that Z1 starts at 0, which was our boundary condition here. And it ends at -2, which was our final time boundary condition. And then note that, so Z2 is defined as the time derivative of Z1. And so when Z2 is positive, Z1 grows. When Z2 is negative, Z1 also decreases. Right? So this is just like a visual inspection that we did indeed solve these differential equations. Okay. Yeah, I think I'll take some questions now, and then I'll wrap this up next time. Yes?
Is Z2 completely unconstrained here then? Because you take the Z2 dot equals -Z1, and then back out what Z2 should be at a different time. You would just be left with an unknown constant. Right? So do you constrain Z2?
In this case, Z2 has to basically is something that always decreases, right? Because the time derivative of Z2 is negative an absolute value. And so if you also inspect this visually, this is what is happening. But if you're talking about other specific constraints on Z2, in this case, we don't have any.
So it can start and end at any value.
All right. So see you on Wednesday. We'll be wrapping this computational methods, and then we'll introduce direct methods. Thank you.